We are now recording. This is section 2.3. The title of it is Continuity.
Can we give a shout out to PT so whenever he watches this?
Sure.
Hey PT.
You're just assuming he's just going to fall in love with my videos and be watching them all the time.
I'll tell him I left him a special present in 2-3.
Okay. You might be offended that I was sharing our conversation. Okay, there we are. Before I write the definition, and I will write, that's where we're going first, because that's really what this lesson is all about. So this is, what we're actually defining here is continuity at a point. In fact, let's not do the quotes. I don't know why I did that. All right, so we want to talk about continuity at a point. Talk to me about what you know about what it means for a function, or when you hear the word continuous, what comes to mind?
No breaks.
No breaks, keeps on going. Madison remembers my very informal definition that I told you last year, which would not be adequate for an actual definition, but it helps you think about it. That anything that's continuous means I can draw it, whatever it is, without picking up my pencil, right? Okay. So let's go back to sine x over x. All right? At 0, a limit at 0 would be, hello? It's not a trick question. We've talked that function to death this week. The limit as x approaches 0 of sine x over x is 1, okay? Is that function continuous at 0?
No.
But what does it have? Okay, but what does it have? A limit. It has, the limit exists there, right? Why does the limit exist there? Finished?
Yes, ma'am.
Cool. All right. Why does the limit exist there in spite of the fact that it's discontinuous there? Because of the hole.
Matters how you get there.
That's right. Exactly. Haney said it. I don't know if he said it loud enough to be heard on these microphones, so I'm going to say it for him. Because it doesn't matter what's happening at the point, it matters how you get there. And from both sides, you get there from the same direction, right? Or you end up in the same spot from either direction. It's a better way to say that. An actually accurate way to say that. All right, so we're going to break this definition into interior points and exterior. We'll start with interior. But before we talk about specifically what this actually says, and we'll say interior point, and I'll abbreviate that. Oddly enough, we abbreviate point PT. How about that, Mackie? But why would we need separate definitions? And because I will tell you that it's this definition is very connected to limits. Why would we need a separate definition for interior and endpoint continuity? Okay, if I apply the strict definition of the limit from the left must equal the limit from the right, yes? How does that make endpoints kind of out of the game if that's our only definition?
Because we're going towards the middle.
Oh, if there is an endpoint, that means I can only get there from one side, right? So it would not be possible to have equal limits from the left and the right, yes? Okay. But on an interior point, which is anywhere between the endpoints, I can look at the left and the right, correct? You with me? All right, so tell me now, that you've had a little more guidance, why does it make sense that you're going to need an interior point definition of continuity and an endpoint definition? If it's connected to the limit, which I just told you it is. That's right. Endpoints only have either left or right endpoint, left or right hand limits, right, depending on which one we're talking about. But interior points have both, okay? So we're going to start with, and I'm trying to decide how much of this to actually have you write. All right, so y equals f of x. So by that notation, what do I know we're talking about? A function, and all that came with that we learned about in pre-cal, yes? Is continuous, and we're going to abbreviate the wording inside here, at a at an interior point of its domain Now I'm going to pause right there and help you understand the significance of that phrase, in it, of its domain. If you think about sin x over x, which is continuous everywhere but at 0, the only place we talk about the limit is at 0, which is at a discontinuity, right? So that's why it's specified that what we're about to say only applies if the function is continuous. And then when I write what I'm going to write next, you'll know exactly why. If, big if here, the limit as x approaches c of f of x. All right, now which limit is that based on that? The limits. The limit. Okay, what's the difference there? The limit as opposed to what? Left or right. And where do I get the conclusion that something has the limit? The what? The left and the right are equal, right? Okay, so by the fact that we've written the limit as x approaches c of this function, we're saying that both the left and right-hand limits exist and are equal, right? So that one little bit that looks like one piece of information is actually at least two pieces of information built in, right? And then has to be equal to f of c. What is f of c? That's right. If I substitute c for x in the function and get a result, that is, it must be equal to the limit I got from the limit as it approaches that value. Does that make sense? Okay? All right. And then we have the endpoint definition. So we'll do a little breakout here and write endpoint. All right. And I'm going to, and obviously you can look back at your book later and see the formal way this is expressed. But we're going to set this up and write left on the left underneath as a little heading. And then slide down the way and write R-I-G-H-T, right, as sort of a little heading. So let's think about a left endpoint. And if you need to, you can kind of sketch one over in the margin. Draw yourself a little finite function that starts and ends, has an endpoint on both sides. Okay? If I want to talk about the limit at the left of your function, what's the only way to ride there if you're riding the function? You have to come from the right. Okay? So if it's a left endpoint, I'm going to be coming at it from the right. And typically, and let's up there beside the word endpoint, put and I'm going to put bracket A, comma B, because remember our typical endpoints we use A and B, or parentheses A. Well, no, we're talking about continuous now. If I have open endpoints, can I have continuity there based on the first part of the definition? No. So we're talking specifically about a closed interval with defined. How do I know based on the brackets that the dots would be closed? Because that's what the brackets mean, right? Just kind of trying to refresh your memory on all those little fundamental details from pre-cal. So the limit as x approaches a, where did y'all say we had to come from? The right of f of x. What do you think it has to equal? How do I write that? Tell me what to write. F of a. Doesn't that make sense? Okay. And then for the right, tell me what to write. Wait, as it approaches what? B. We're on the right endpoint now, right? Okay. The limit as x approaches b from the left of f of x is going to have to equal what? F of b. Does that make sense? Did you? It's kind of interesting because just like I pointed out last year in your pre-cal books, remember I said sometimes these authors love to throw stuff at the very end of the assignment that you're like, where did this come from? But typically when you have that moment, it's kind of leading you towards where we're about to go. okay? Because everything we do builds, so they're trying to show you the direct link there. Any questions about that before we write a little bit more about it, and it's sort of a subscript to it? If a function is not continuous at a point, we say that it is discontinuous at C. Do we need to write this? And what is that point called? A point of discontinuity? Okay, yeah. That's just a little refresher from pre-cal. All right, here's some more pre-cal refreshers. All right, so let's go now to discontinuity types. What's the one we've talked most about this week, probably? Whole, all right? So let's start with a whole, and that's what we will call it most of the time. But what is its more formal name? What did we call it last year? Can we patch that? Remember, you can patch that, right? Because how did I tell you last year to decide whether or not it could be patched? That's right. We only have point size patches, right? And I don't know that I used that language last year, but it's the same idea, right? This is a removable discontinuity. It is the only removable one. And I'm going to abbreviate discontinuity there. Now remember, the fact that it's a whole means that it is defined up to it from both sides, kind of like on sin x over x. That is to distinguish it from an open endpoint. Okay? All right. Anybody got another one for me? Jump. And where does that typically show up? Piecewise. Okay. So probably mostly on piecewise. There is one parent function that the step function, which also has other names. But we'll call it step here, right? Piecewise and step functions is where we typically see those two discontinuities. And we've got one more that you really learned well last year, and then there's another one. I think we mentioned it, but it probably didn't really register at the time, but we've actually talked about it this week. There's two more, so what's one of them? Yeah, the vertical asymptote, and we'll just put VA for that because that's what we do most of the time. But your textbook will refer to it probably more frequently and maybe all the time as an infinite discontinuity. Remember that? Now, I'm pretty sure we talked about this last year. I know for a fact I've talked to several of you, if not the whole class, about it, and that is an oscillating discontinuity. And I doubt that would come to you on a Friday morning. All right? Y'all, who can tell me when and in what context we talked about an oscillating discontinuity this week? Sine and cosine, right? Because, and in the context of any function that had either one of those, we talked about the fact that just because you get a really big number that you've plugged into it, you still don't know much. You don't know any more than you did knowing that the sine function is trapped between 1 and -1, for instance, right? So it doesn't do me any good to know that we're at 1 million pi. Well, maybe it does, because then that would be a reference angle. But do you see what I'm saying? Like, just the fact that it's a huge number doesn't specify a direction the function's going to, because it does the same exact thing forever. So we can't predict a designated limit at either end. Yes? Those pretty easy, simple. One of the things that this section does is that you will be given some piecewise functions. If we had a little more time, I would actually do this exploration with you, but I will just point it out to you. If I have a function that is defined everywhere but at a particular value, like sin x. So, in fact, let me just do a quick example of what I'm trying to show you here, all right? So let's look at our good friend, and we'll just call this an example. It's not technically even really an example, I don't think. But let's look at our good friend by now, sin x over x. Because there's actually three ideas we need to clarify and clean up here. All right. And I'm going to take a big deep breath because I have a feeling I already know how you're going to answer this. Is this a continuous function?
Yes.
No,
No, because it could be at
It's got a
zero.
hole in the very top.
Madison, has anybody ever told you you're just adorable? Okay, so we have forgotten that very important definition of a continuous function.
It's continuous on its domain, so if you take zero out.
Which means what?
It
It
is continuous.
is a continuous function. Right? It has a discontinuity, doesn't mean that it's not a continuous function, okay? So let's get that straight, all right? And that's why we're gonna keep coming back to this function, because now that because this is a very emphasized function in calculus in that it just shows up just when you least expect it. So let's kind of make some notes here, all right? So continuous on an interval means that there are no discontinuities. And this seems counterintuitive, but there are no discontinuities. A continuous function, on the other hand, as Clark so aptly put it, a continuous function simply means that it is continuous on its domain. I'm starting to write in hieroglyphics, sorry. Don't need an S there. Continuous on its domain. So do you see the distinction? So if we go back and rethink the question, is sine x over x a continuous function? The answer is an emphatic yes. Because everywhere in its domain it is continuous. Because didn't we say its domain when we were going over the quiz? Because it's the same as cosine x over x. Makes sense? Okay. All right. So if you have a function like sine x over x, it is easy to produce what's called a continuous extension. And you'll have a couple of these to do and I don't even remember if it actually calls it a continuous extension. It may word it slightly differently, but it's talking about this idea. Okay, so back to the example we're actually looking at here. So for f of x equals sine x over x, we have agreed that this is a continuous function, but it has a discontinuity, right? And Madison so graciously shared with us that we know we could fix that because we have a kit full of little points that we can stick in places like this, right? And that's what makes it removable. All right. So I'm going to redefine g of x to express this function as continuous. Okay, so that it becomes continuous. All right. So anytime you're doing this, your first line should be the function itself. And then remember, you put a comma, and then behind the comma, you say, where does this apply? Okay? Well, where is sine x over x already continuous on its intervals? It might be easier to say where it's not. It's not at 0, but everywhere else it is, right? Okay? So when you're doing a piecewise definition, it's a lot easier to write because this is the conditions where this applies. Then we're going to say x does not equal 0. So as long as x does not equal 0, we're still using our function, which is pretty much everywhere, right? But now I need to redefine what happens at that hole so that it's no longer a hole. So what would plug the hole? What coordinates? So I'm going to put the y coordinate here because that's what this is. Remember, because g of x is y, right? So it's 1 if x equals 0. Does that make sense? So the continuous extension is the 1 if x equals 0. Okay, and the piecewise function notation is the best way to write that. All right, theorems. We've got a couple of them, actually 3 of them. Theorem 6. Properties of continuous functions. I'm going to abbreviate that the whole way. Okay. Who can give me, and I'm not gonna write, yes,
What's that stand for?
properties of continuous functions. Okay. Who can give me an example, well, in fact, let me make it simpler. Give me a really simple continuous function. A one term. X, did you say X? Okay. We'll start with X. Alright, is X continuous? Alright, somebody give me another, even simpler function. Even simpler?
Y equals
X
20.
squared is not
Y
simpler than
equals
X.
20.
How about 2? So, what is X? If I graph it, it's a line, it's a particular line, it has a slope of 1 goes to the origin, it's that diagonal line that a lot of things refer to, right? So it's like the mother of all lines, yes? Okay, how about 2? Horizontal line, yes? Okay, so then if I write X plus 2, so I've just added 2 continuous functions together, 2 linear things together, I ended up with another linear thing, yes? X plus 2 is now in what form? Slope intercept, right?
Yeah.
So it's still continuous, alright? But what if I change that plus 2 to a minus 2? Would that change the story? Not at all, right? Okay? So we've just discovered by that very simple set of examples that if I add 2 continuous things together, I get a continuous thing. Agreed? What if I subtract it? Same thing. Okay? Well, what if I multiplied X and 2? Same thing. So now we can include multiplication in our thinking, right? How about if I divide 2 by X? Okay? So here's what we're going to do. And obviously, again, when I do quick paraphrases of theorems, you should, as needed, refer back to the formal definition in the book, okay? So in the book, we cover 5 of them, and I'm going to list them for you, and you tell me how many of them we've already addressed. Sums, differences, products, constant multiples, and quotients. We've got all of them, haven't we? Okay. Now we did very simplistic examples, but the good news is Theorem 6, the properties theorem, tells us that all that applies to everything we just said. Okay. So everything we just said in the simplest case works even the ugly ones, right? So, and that's really important because it's the ugly ones that you're going to need to know this for. So like if it's e to the x times x, would that be a continuous function? Based on what we just said.
Yes.
Assuming that what worked with linear stuff works with those 2, why would it? Because what do we know about e to the x? It is a continuous function, right? And x is a continuous function, so their product will be, right? So what this theorem tells you is that sums, or we'll say the sum, we'll do it that way. The sum, difference, product, and I'm going to break the quotient out as a separate thing. Why would we need to do that? Because it depends on what's on the bottom, right? Okay. So the sum, difference, product, and constant multiple of continuous functions is continuous. And that summarizing takes care of the first 4 of these 5. And the only thing we haven't dealt with is the quotient. And so now I want to write this and I want you to tell me how we need to end it, okay? The quotient of continuous functions is continuous. And tell me why I cannot stop there. What do I need? What wording should I probably use next? Okay, as long as, let's say it that way. As long as the denominator does not equal. I can't do that, it exists. I was gonna use the D and E. Does make sure I'm still recording. Does not exist. Or I'm sorry. I had D and E in my head and then got the interruption that I'm pondering. Does not equal, we'll use the equal symbol there, 0. Right? Okay, and of course the theorem uses F's and G's and C's and whatnot, but I think you've covered enough to know that that works, all right? And I'm pretty sure we looked at that idea last year, didn't we? So that's not new, yes? No. Sure, if you say so. Pretty sure that's a pre-cal concept. Okay, all right, composite of continuous functions. I know we talked about, I could actually pull y'all's old tests out and prove to you that I'm right, but who wants to do all that? Of course you do, Mackie, of course you do. Okay, so composite of continuous functions. What is a composite? I like that. That's use of vocabulary. Stuff that's put together. That's not a very mathy definition. I would like a mathy definition of composite functions. How do I build a composite function from f of x and g of x? No, I don't want to set it. You can only use f of x and or g of x. F of g of x or there you go. So what are we really doing there? You're plugging one function into the other function, right? So the function of one becomes one function becomes the input of the other. Yes, that's what a composite is. Just as a refresher. All right. So if f is continuous, at C, and G is continuous at f of C. Now I'm actually using the formal wording here because you'll need to revisit this one for it to become completely assimilated into your way of thinking. Then the composite, which I'm going to skip the words the composite because G of f of x, that is a composite, right, by its notation, is continuous to C. Now, as you finish copying that down, I would ask you to, the sort of like fast food version of this is the composite of continuous functions is continuous. Now, of course, just like I could say the quotient of continuous functions is continuous, but there's a built-in caveat there, and that is that the denominator can't be 0, right? In the same way, if I'm looking for g of f of x or f of g of x, obviously I have to be able to substitute the value I'm looking at into the inside function to get a value to plug into the outside function. Do you see what I'm saying? So that's another caveat that's implied by your knowledge of how functions work. Okay? Questions about that? All right. Let's jump to our final theorem for this lesson and the week.
Yes.
Amen.
Yes.
Now,
Praise God.
yes. Okay, this is the intermediate value theorem.
Yeah, I've heard that before. We learned that.
A lot of what we talk about you should have heard before because you were in my pre-cal class. Intermediate value theorem for continuous functions. Now, we will never again refer to this function in that very wordy way. We will call this the IVT. Put a box around that. because unless you just really like to hear yourself using big words and names, you won't say the intermediate value theorem for continuous functions. You will say, doesn't the IVT say? That's how we will refer to it, okay? All right, and when you apply it, you're doing the same thing. So let's say y equals f of x is continuous on, and again, the book uses the words here, but I don't think we need them. I'm going to write it and y'all tell me what this means. Bracket A, comma, bracket B. So what would the words be for that notation? On the, what kind of interval is this? Closed. How do I know it's closed? Brackets. There you go. All right, so if I were to draw a picture of this, what do I know about my endpoints when I draw them? They're filled in, they're not open, right? So y equals f of x is a continuous function on AB and takes on, and this is the literal wording of the theorem, every value between f of a, and as I write that I will pause and ask, what is f of a?
Function of a
What?
Why?
The Y value.
It's the y value when x is, thank you. Okay, so this is our y value, because the whole point of this theory is going to zip right over your head if you don't understand that, between f of a and f of b, which is the what? Y value when x is b. Okay, so in other words, the y value is at the endpoints. So let's say my left y value is 4 and my right y value is 10. What do we know so far? When it says it takes on every value between 4 and 10. Somewhere on that interval, any number you name that is between 4 and 10 is hit by this function, right? It comes as an output. Does that make sense?
Yes.
Okay, that's what that says. All right? And then it says, in other words, and I don't know whether we're going to write that part or not. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c in a b.
Yes.
Does that help you?
You gotta slow it down. If you say that fast, I'm gonna be confused.
If y sub 0 is between f of a and f of b, then y sub 0 equals f of c. Now let's pause. Okay, what is f of c? That's right, it's another y value that's not the endpoints, right? Okay, and y sub 0 is the f of c, which means it, because it already said that it's between f of a and f of b. So if I use 4 and 10, what does that tell me about f of c? It's a number between 4 and 10, so it could be like 7.83, right? You with me? Okay. For some c in the closed interval a to b. Okay, so that c value is just an x value in between. All right, now we're going to draw a sketch of this. So let me get my straight edge tool, see if I can manage that on this Friday morning.
You see how much we got when you slowed it down? You said it way too fast for tomorrow.
I'm sorry, I thought y'all were smart enough to follow me. No, just kidding. No, actually, I thought it was Friday, and I was trying to get this done before y'all go. That's really what that was about.
Get a sandwich there, boy.
That's not horizontal enough. Okay, here's what we're looking at. So we're just looking at the first quadrant, and I'm going to draw this curve, and this is very similar to the one in your book. So when you refer back to it, you should be able to match what we write here or draw here to what's in the book. All right, so we have this function that starts at the point a f of a. You don't have to label that yet, and it's kind of a almost S-shaped, or like you took a piece of a cosine or sine graph and stretched it vertically and sort of twisted it a little bit. Make it a little off kilter. All right, so we got a dip and then a peak, and we've got closed endpoints. Okay, so let's emphasize the closed endpoints by putting some closed dots on the ends. All right, and then we want, let me see if I have a dash line tool here. Of course I don't. All right, so I'll just draw these in a different color. All right, now, so my first, my left endpoint, what do we call that x coordinate? A. So then when we go back to the y-axis there, what is that point coordinate? F of A. Is that yellow hard to see? I'm gonna switch to orange for the other one just to color code it. All right, and then on the opposite end, what's the x coordinate there? B. And if I draw my horizontal back to the x-axis, well, that's a sad horizontal. All right, close enough. All right, if I draw horizontally back to the y-axis, where am I? F of B. All right, so on the vertical axis now, we see our little range of values from F of A to F of B, don't we? Okay, and then the A to B would be the range of x values. All right, so now, based on that theorem, and I'm going to throw this in here in red, if I drop in somewhere in the interior another little vertical indicator and stick a C down here, because that's that point in the interior that you're going to be asked to find, okay, and then come back to the y-axis, what has to happen? That value has to be between those points, and that's what intermediate means, right? Between. All right, so what will I write in between these two? F of C. So there's the picture to go with that theorem. Now, what this picture shows that the intermediate value theorem doesn't guarantee you is that I could still have values, and that's one of the reasons I like this picture. Notice the little peak up there at the top on the right? Is that between F of A and F of A and F of B? No, that's left that interval, right? The intermediate value theorem just guarantees you what's happening between the points. It doesn't say that it can't go higher or lower. You see what I'm saying? So I could have like super wild oscillations that go way up and way down and come back to those endpoints. Well, all that I'm guaranteed in the intermediate value theorem is that the values that are between the two y's. Does that make sense? Okay. Excellent, productive day. Take a stab at the homework.